these is whatever number you are approaching. Like, so right here, we are approaching 3. Sometimes I like to sort of draw myself a vertical line down through here, through 3 to kind of get, like that's where I'm going to, right? So if I start over here on the left side, and I go to where my x value is 3. So if we're thinking about it, like here, my point is 1, 3, right? Right here, my point is 2, 2.5, right? And then like maybe here, my point is 2.52. No, 2.5. I need my pen to be smaller. 2.5, 2.2, maybe, right? And then I could go like right here. And then my point might be like 2.9 and 2.1. You know, I'm just guessing, right? So I'm getting like my x coordinates are getting closer and closer and closer to 3. What would be even closer than 2.9? 2.99 or 2.999 or 2 point a gazillion nines, right? Even at 2 point a gazillion nines, you're not at 3 yet. But you're getting closer and closer and closer and closer to 3. In this graph, do you actually ever get to 3? You do not, because you have an open circle, which tells you you can't go here, right? But you can go as close to that as you can. So, like, any of y'all spend the summer babysitting some kids, like, and you tell them they can't touch something, or they better not cross this line? What are they going to do? They're probably going to cross it and get themselves in big trouble. But let's say they don't. They are going to, like, not be in trouble. These children, their limit is approaching the line, right? They get, like, if I say don't cross this line, then my youngest one is going to be, like, millimeters away from that line. He's probably eventually going to cross it and get himself in trouble. But they're going to be, you know, like, or don't touch your brother. And then you look, and one of them's over there, like, just, like, that close to touching your brother. Yeah, that's what's happening with this, you know, here. You're getting really, really close, but you're not actually there on this graph. For limits, it doesn't matter if you get there. Perhaps if this is happening at my house, I say, don't touch your brother, and I turn around, and Henry's got his finger like that close to Hunter's face, or the other way around. It really doesn't matter. They love to fight so much. It's their favorite thing in the world. You know, chances are I'm going to say it doesn't even matter. I'm like a limit. It's close enough. I'm done. It's what you are approaching. So in this case, as x gets closer and closer and closer to 3, we go to that single point, right? And so we're not at 2, but we're real close to 2. Your answers for limits always have to come from the y-axis. It's the y value that you are approaching. So in this case, and it has to happen from both sides unless you're talking about a one-sided limit. So in this case, I have a hole in the graph right here, but my limit still approaches 2. Now, what about if I ask you for f of 2? Oh, wait, yeah, probably. I didn't mean to right there. What about if I ask you for f of 3? Change my question. It does not exist, right? And so we will call that undefined. So you can have a situation where the graph is undefined at that point, but the limit still exists because you're getting closer and closer and closer to that point. Not always. A lot of times it's what they'll ask us about because it's like an interesting point. So they don't ask you about like this point way over here that's boring. They ask you about like the things where funny things are happening on the graph. But there's not always a hole. But it's one of the options. Another option is what you've got on the second graph right here. Okay? What is different about, I mean, obviously they're different graphs. This one is a parabola, the other one is an absolute value. But what else is different about the first graph and the second graph? We got this point at 3, 4, right? So if I wanted to find G of 3, what would it equal for this graph? It's going to be 4. That's where you've got your like closed-in circle, right? So G of 3 is 4. This function is defined at 3, and the answer is 4. But is that what we approach as we go from each side? It is not. Because like if we think of following this graph over here, you know, we're getting closer as we go from the left side, we're approaching that open circle, right? We're getting closer to that open circle. Same thing from the right side. We're not approaching 4, we're approaching that open circle. So the open circle is what we're getting closer to, and its y value is 2, and that is why 2 is the answer to this one. Okay? So for limits, you're thinking about what you're getting closer to, not necessarily what the function is defined as. It can be undefined. It could have a different value than what you're given as your limit. Or you could have a boring example. The last graph is the very boring example because we're talking about approaching 3 right here. And if we look at h right here, what is h of 3? Is 2, right? Because this graph right here is just a solid line, so that means it's a closed circle right there at 2. What do we approach from either side as we get our x values get closer and closer to 3? We also approach that same point, and its y value is 2. Yes? Limits are just talking about what you're getting closer to. So this is the limit as x approaches 3, not x equals 3. So even if it's defined the same there, because we're using limit notation, it's still what we're talking about getting closer to. So you're sort of thinking about that same thing. Even though this is defined, you could still look at 2.9, 2.99, 2.999. You could get closer to that point, even though you can actually get to that point as well. So all 3 of these are examples of where limits exist. So limits will exist at all 3 of these examples. You can have a hole in the graph, maybe that's defined somewhere else, not defined somewhere else, or a continuous graph, one that doesn't have a hole, and those are all going to have limits. Okay? We're also going to have places where limits do not exist, and we'll talk about those in a minute. Okay? If we look at example 1, in order for you to have a limit that goes from both sides, which we haven't looked at like a ton because we mostly did this for end behavior, right? We mostly looked at x approaches negative infinity and x approaches positive infinity. So if you do not have a plus or a minus sign behind these things, that means we are approaching from both sides, right? So if I look at example 1 for A, it's the limit as x approaches 4. So sometimes what I like to do is I like to go in here and I like to put myself a dotted line at 4 so I can kind of picture that x value that I'm trying to approach, right? So if I start over here on the left side, technically what I do is I go down here, then I got to jump up here. Really, you only want to look kind of close to that line. That's all that really matters because whatever's happening over here is not that important for a limit at x approaches 4. But as I approach here, I go to that open circle. So from the left side, I go to that open circle, right? From the right side, do I go to that same point? Yes. So even though there's a hole right here, I can look over here, and that y coordinate is my answer for that limit. Okay. I'm going to skip down here and do C next, just because C is also at 4, and I'm going to need to erase this to do the next part. So I've got G of 4. So G of 4 is not asking me for a limit. It's asking me for the value of the function at 4. What is that going to be for this problem? What do you think, Connor? 2. Right? It is that closed circle. It's where the function is actually defined for that. So those two don't match, and we'll talk later when we talk about continuity. This graph is not continuous. The limit exists, but it is not continuous because of that hole. They don't have to match. All you have to have is from both sides. They have to go to the same point when you're doing the limit. Okay? Now let's look at the next part. Switch to green. And this one's x approaches positive 1. Okay? From the left side on this graph, I'm approaching that open circle right there as x approaches 1. Its y value is 1. Do I approach that same point from the right side here? I do not. I'm going to different points. Like if I think of mirroring this with my hands, like this is going down, this is going up. When this happens, you can't have a limit. Not from both sides. If it's a one-sided limit, we could still do it. But this is a double-sided limit, so I cannot do this. To have a double-sided limit, you've got to match up. Your two pieces have to match. Miss White used to say it was like E.T. I don't even know if y'all have seen it, because, I mean, that was like when I was a kid, so, but excellent movie. If you want to go watch it, they touch fingers like that. Me. For this, for limits, we're going to say does not exist. Now, I'm not going to encourage the use of this, but I know as all stellar mathematicians, we don't like words that much, and we want to use as few words as possible. This is a good time for me to warn you that you don't want to abbreviate things on the AP exam unless it is an official mathematical symbol. So, lots of students start doing this. They start doing DNE, does not exist for this. I understand. I, as a mathematician, also do not like words and prefer the shortest possible way to write something down. But I wouldn't do this on the AP exam. I will say that one's common enough that I think they're probably going to take it from the things that I have graded. But I would not do this on the exam. If you do it on your homework, make sure you know what it stands for. Like, because acronyms were like terrible. We're like really guilty of using acronyms and then forgetting what they stand for. Like NASA is an acronym. Couldn't tell you what NASA stands for. National Aeronautical Space Association, maybe. Administrate. See, too many A words it could possibly be. ACT is an acronym. SCUBA is an acronym. Like there's so many acronyms that we use them so regularly we forget what the words really are. On the real thing AP exam, please just go ahead and write it out. It leaves so much less room for error. It would be tragic for you to not get points because you use some sort of abbreviation that they don't know. For example, here's a really good one you better not use. Bobo Botno eats DC. It's some sort of crazy thing. I don't even know where it came from. I'm pretty sure it's going to be, like some southern words. Like you get up north, they're not going to be Bobo Botno eating DC stuff up there. I don't know where this came from, but don't put it down. You can talk about what it means, and it's helpful, but don't put it down. So that's just my warning right here for the AP exam. Try not to abbreviate if possible. But I do kind of get it on homework. I do know what that means. And it may have even been done on some answer keys. So forgive me if I did that. So let's look at 2. Sometimes this throws kids for a loop whenever we start looking at places like 2, because at 2, this is actually like what I would call a boring point on the graph. Nothing interesting is happening at 2. It's just the line, right? But if it's just a straight line, that is a solid dot right there. And you're approaching the same thing from both sides. And G of 2 also has that same value here. It's a boring point, but the limit definitely exists here. You're just going to get the y coordinate. Will be 1 for that. Mm-hmm.
So like on B, because the hole is there, but there's a dot where, like, from the left, it can't happen. But on this one, because there's a hole to the right, it's still going to happen. Like, you can reach it from both sides.
For which one?
I just mean, like, so for B, like, the hole is there, but there's a point out at the top. So
yeah, and yeah, the difference is like, so the difference between there on B is it like your 2 sides are going in different directions, like you're not going to the same point on both sides, whereas for A, there was a hole there too, but both sides went to that same hole. So for you to have a limit, both sides of the graph have to go to that same point. It could be a hole or it might be just like a solid dot, but both sides of that graph have to meet up. And if they don't meet, if you got like a jump in the graph, the limit's not going to exist at that point. Okay. Now, we also sometimes look at one-sided limits. So he's used that same graph again. So at 1, the limit does not exist, but the one-sided limits can exist. So if I'm looking at limit as x approaches 1 from the left of g of x, that means, 1 is right here, and I'm getting closer and closer and closer to that dotted line from the left side. It takes me to this point right here. So from the left side I approach this, the y coordinate of that there is 1. So I would say that the limit from the left is 1. But from the right, if I do the same thing here, if I go from the right side, then I go up here to this point right here. Its y coordinate is 4 right here. So the one-sided limits exist in this case, but the limit from both sides does not. He's got a note here. Be careful. From the left does not mean you're moving left. It's the opposite of that, right? If you're coming from the left side, you're actually moving to the right side. So watch out for that. And let's see if he puts this. Let's add this in right here in order for limit as x approaches a of f of x to exist. So in order for that to exist, the limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x. So the limit from the left and the right have to be the same for you to get the answer, or to get that same answer from both sides. Okay, here. All right. I'm going to let you guys try example 2 right there on your own. In fact, yeah. Try 2 there. Okay. For A, you should get 1. B, especially because of space, I'm going to do what I told you not to do here. does not exist. We're just going to make sure we, in our head, are saying does not exist for that. C is going to be 0. D is 1. E is 2. I am doing these in my head, so if it seems like something is wrong, let me know. F is -1. G is does not exist. And H is, okay. I'm glad he did this right here. I didn't work through every problem, so I'm glad he did, but I'm glad he did this here. What would you say about H? Like, what did you guys put down for that? Okay, very good. Undefined. As far as language goes, if they ask you to evaluate the function and it's not there, you're going to call it undefined. If you're talking about a limit, you say it does not exist. Those two things sound almost the same. It's one of those things like they might grade it the same on an AP exam. Like they might accept it and be like, close enough, because sometimes they will do that whenever they put those things in the rubric. But technically, if you're talking about the value of the function, you say it's undefined. If you're talking about a limit, you say does not exist for those. So that's the difference in those that language right there. All right. Let's see. We need to keep moving on. Let's do. All right. 3. I want you to come up with, from this picture, a limit that exists, a left-sided limit, a right-sided limit, and a limit that does not exist. Okay, there's lots of options on this. So what you write for this could be different than what the person next to you writes, and you could both be correct.